So the question becomes, what happens if I have some weird looking improper integral, like, I don't know, let's go 1 plus e to the negative x over x dx. What if I throw this at you guys? All right, so something like this. What am I going to do with this? Right, because it's not one of these guys. It's not one of our freebies over here. Remember, we got ourselves a little p integral, which just makes me laugh to say. Right, if p is greater than 0, if p is greater than 0, sorry, if p is greater than 1, sorry, I got it flipped around, then I know that this thing converges. Otherwise, converges if p, what? You guys got to yell at me when I do stuff like that. This is going to be if p is greater than 1, else it diverges. Sorry about that. All right, so I don't have that in this situation. However, there's something that's really, really useful, and it's called the comparison theorem. Let me show you what this guy is. It's awesome. And we use it over and over and over down the road as well. Okay, right now it's going to look like kind of one of these boutique theorem that it's like, why do we keep using this? Or when do we use this? Well, we're going to use it a bunch down the road, whether we want to or not. Comparison theorem says this. It says, suppose, excuse me, that f of x is greater than or equal to g of x, which is greater than or equal to 0. Okay? Now, that's just the supposition. So can you visualize functions where f is always bigger than g and g is always bigger than 0 or greater than or equal to, right? So they're always positive, and g is kind of, this smells kind of sandwich theorem-y-esque, if you will. Now, think about this. If the integral from 1 to infinity of f of x dx converges. Now, let me talk a little bit about this first and foremost. Do you realize that this one chunk doesn't really matter? This could be from 17 to infinity. It could be from 0.8 to infinity. It could be from who cares to infinity, as long as we don't cross across a vertical asymptote, right? Because if you think about it, let me just do a side note here. If I do the integral from let's go 18 to infinity, right? Don't we know that this is equal to the integral from 1 to infinity minus the integral from 1 to 18, right? They're the same thing. Does that make sense? So I can always do a substitution here, even though we won't. You don't have to do that. We're not afraid of that. Yeah, I just wanted to dispel any confusion that might cause if we start out at a number that's different from 1. All right? If the integral from 1 to infinity of f of x converges, what does this imply about the integral from 1 to infinity of g of x dx? What must it do? Well, g of x is always less than f of x, so what does that tell us? That means that if f of x is heading for infinity, and that garden door that I keep talking about, if this is f of x, closes quickly enough, and g of x is always wedged in between those two, what has to be true of g of x? Well, you guessed it. It converges. How's about if, let's change colors again so we stay consistent. How's about, so that's going to be 1, this is going to be 2. How about if the integral from 1 to infinity of g of x diverges? Now again, if I stick a g of x in here, if the garden door doesn't shut quickly enough and g of x diverges and f of x is always greater than g of x, then what has to be true about f of x? Does this imply about the integral from 1 to infinity of f of x dx? Well, it has to diverge. Now, an interesting question is, well, let's think about this. What if, so let's just do this as an asterisk. What about if the integral from 1 to infinity of g of x converges? What does this imply? Well, if g of x converges and f of x is always greater than g of x, what do I know? I don't know anything. I don't know anything, so there's not enough info. Similarly, if, let's do this, another star, if the integral from 1 to infinity of f of x dx diverges, well, if f of x is greater than g of x, okay, clearly the garden door didn't shut quickly enough on the horizontal asymptote for f of x, but g is less than f. So we don't have enough information. Not enough info. All right, so let's get back to this integral right here. Let's come over here and go to the integral from 1 to infinity of 1 plus e to the negative x over x dx. This is clearly not one of these guys, is it? This isn't 1 over x to the p. If it were x to the p, we'd be stoked, right? However, look really closely. What do you notice about 1 plus e to the negative x over x? Well, think about it. Don't I have a home base that I can work with, a p integral, if you will, that I can work with, that I can compare this to? How about 1 over x? What is the relationship between 1 plus e to the negative x over x and 1 over x? Well, e to the negative x, while intimidating when first looking at it, do you realize that it always spits out positive numbers? Always. And 1 plus a positive number is always greater than 1, so this guy is always greater than 1 over x, right? So what does that imply? I don't even have to say greater than. I could say greater than or equal to 1 over x, even though it's never equal to it, right? So what does that imply? So what we would write is, by the comparison theorem, I can write CT, all right? Since, now this is where we're going to get a little lawyer mathy here. We're going to talk like lawyers. The integral from 1 to infinity of 1 over x dx diverges. Now we got to give a reason, and the reason is that p equals 1. It's not greater than it's not greater than 1. Remember, we can only say that 1 over x to the p converges if p is greater than 1. And since p equals 1, this guy diverges. And 1 plus e to the negative x over x is greater than or equal to 1 over x on the interval from 1 to infinity. We know the integral from 1 to infinity of 1 plus e to the negative x all over x dx also diverges. Okay? Let's do one more. I'll be quick, I promise. How about this guy? How about the integral from 15 to infinity of 1 over x squared plus 3x plus 1 dx? How about that guy? Again, it doesn't look like one of these guys. If it looked like one of these guys, I'd be stoked, right? However, let's look at the relationship between 1 over x squared plus 3x plus 1 and one of these guys. What can you tell? Well, remember, out at infinity, these two terms right here, 3x and 1, don't really amount to a hill of beans compared to x squared, right? So why don't we compare it to x squared and see what happens? Don't you agree that if we're dealing with numbers from 15 to infinity, when I plug those in, 1 over x squared plus 3x plus 1 is always going to be less than or equal to 1 over x squared, right? This is a bigger number in the denominator, which produces a smaller fraction overall. So we say since the integral from 15 to infinity of 1 over x squared dx converges, then we give a reason, p equals 2, which is greater than 1. Okay, or you could just simply say, if you wanted to, you could say p is greater than 1, and I'll understand what you mean, and that's completely acceptable. And 1 over x squared plus 3x plus 1 is always less than or equal to 1 over x squared on the interval from 15 to infinity. We know by the comparison theorem that the integral from 15 to infinity of 1 over x squared plus 3x plus 1 dx also converges. Isn't that clever? That's really, really clever. And yet, it's so intuitive. Duh, if I've got a function that converges, f of x at infinity, right, whose integral converges, then the function that's less than it, that's wedged, sandwiched, if you will, it's almost like a squeeze theorem for integrals, isn't it? If it's squeezed in between those, then this guy has to converge. If this guy diverges, then this guy has to diverge because he's bigger. All right, so you are going to have to lawyer up a little bit as far as your notation, as far as the way in which you make your case. You're going to have to speak a little bit of math speak on this guy. All right? All right, I hope that was helpful. I hope it was useful, and I'll see you guys tomorrow in class. Have a really good day.